And okay. How to switch the display? There. Uh, um, sh- command 加command 加二是吧？或者 F2或者 R，都不是
全屏那个
对，全屏那个 PDF，且要 share screen 这个 PDF。
PSP 应该是直接这样。
好吧，就我就硬搞一下。但是嗯嗯等下啊，嗯，我以为嗯嗯这个啊。And so can you guys see the screen all now? Is that good? Because I cannot turn on the like display like screen. So is that all right? Okay. And hello everyone. Welcome to the DSI like 5207 Modern Deep Learning. My name is Xinyi Yang, and I am an assistant professor in the department. The fun fact is that it's my ever first lecture in my whole entire life, and also this is a new course, like start from this semester on. And also this is the first lecture of this course ever. So I think it's a good timing to talk about this topic because it's actually about modern. Like it needs a young teacher to teach this kind of course because like if you ask an old professor about the same topic, he will say nothing about it because he does not know the entire domain. Today's lecture will divide it into three parts. First is an introduction about the topic, is then overview of what we'll talk about through the whole semester. And the second part is about linear models. It's basic, the most simpler neural networks ever. And the third part is about the tutorial and coding part. And I will talk about how to do your homework, how to submit it. First, like let's get a very brief introductions. Like if you talk about someone, what is AI 10 years ago, he may does not know. But through a series of breakthrough, you see that AI now comes to the center of the stage. Like here are some of the most important milestones here. First is 2017. It's about AlphaGos. You know that it is the first time that we show that the AI model can beat human. Even if it is the world champion, that it can solve the hardest game of human history, like the game of Go. And sometimes at that times the media says that the human will die from the AI, but now it still survives. The second breakthrough is the ChatGPT. Everyone knows. It's that I still remember it's at the end of 2022, and even if it's not the first large language models, but it is the first time that a large company or a very good product has show in everybody's mind. And now even if you ask your parents what is ChatGPT, they know. And from that day on, the OpenAI becomes the most success company in human history. And this is quite time ago, like 1 year ago, like DeepSeek comes. It is first Chinese company that released this open source model to the public. That they see that open source model can even match the performance of the closed ones. And very importantly, it can support the ability of reasoning. It means that except for like output the results, it can also output some intermediate like steps, how to solve the questions. And from that day on, like you can see that in NVIDIA, they lose trillions of dollars because that Chinese company, like they release very cheap models. Like they only use less 200 times less money to train such kind of models. Those are some of the milestones, but now you do not see those AI models as some magics. You see that it's every day around our lives, from like video generations, healthcare, robotics, AI science, metaverse, self-driving cars, and large language models, and AI coding. You use AI every day, everywhere, every time. And here we can try some of the latest AI models like Doubao. Like we can ask for example, you can ask him like what is PolyU famous for? And it shows that it's thinking about this and what is Hong Kong PolyU is famous for, and he will get through all the resources online and give you results. Maybe the QoS ranking is not so accurate, but it shows most of the like subjects and department and like we are good at. Also, it's quite convenient. Like we can ask him to build like a website for our class. Please wait. Or AI. As long as I input some prompts, like it from the subject name has some clues of what will be covered in this course. Like he will go very quickly through all the resources, and you can see that it's programmed in like HTMLs with a lot of CSS decorations. Like in the end, it will give us quite like a ready to use website. Like you can also make up some course syllabus. Like sometimes when I like prepare my courses, I will use those tools. Like maybe wait a few seconds, like we can go back to our slides. So we see a lot of those examples everybody's using today. I do not need much time to introduce all those applications. But I think quite important is, although they are all called artificial intelligence, the essence of those applications is what we know is deep learning. And in the whole universe of artificial intelligence, the deep learning, we need to trace back to the point why those deep learning are so important. From the whole picture of artificial intelligence, and there is a main subject called machine learning, like it uses the data to learn a model such that the model can make prediction on the test set. And the machine learning can be divided into some subcategory like supervised, unsupervised reinforcement learning. And deep learning is such kind of machine learning algorithm that use neural nets as its models. And this course, we will cover mostly on this part. We'll cover mostly on some supervised and unsupervised learning algorithms that those modern application uses. And if you see through what is called deep learning, they will use this kind of term. They use multi-layered neural networks, and they're trained for large data sets. And we will go through later to see why these multi-layered neural networks are important and why they need such kind of large data sets. And if you do not believe that like deep learning is quite important subject right now, you can look at the Nobel Prize. And Nobel Prize is like not one of, it is the most important prize of human history. And 2024, the Nobel Prize in Physics gives to Geoff Hinton and John Hopkins. And they are exactly for their invention and discovery of machine learning with artificial intelligence. And also at the same years, the Nobel Prize in Chemistry goes to DeepMind for their invention of AlphaFold. They can predict the protein structure from the RNAs. And it does not go to those technical guys. It goes to the CEO of DeepMind. And if you ask Geoff Hinton, is he a physicist? He will say absolutely no. And even from his interview with those TV shows, you can see that he never say he is a physicist. He's just someone who do deep learning. Also, if you ask the CEO of DeepMind, is he like chemist? I will say absolutely no. No, he will not. So now deep learning is no longer just computer science. It's now an engine of modern scientific discovery. And today, we will see that actually this kind of deep learning techniques becomes a must know of our generations. If you do not learn some AI or deep learning techniques, you cannot find a very good job, and you will, if you do not learn, you get left behind. And there are some personal reasons why we should learn this. Like if you search online, and those AI engineers or deep learning engineers are among the most high-paying jobs everywhere. Like I search, I see that and survey for the United States, the annual salary is around 200K. It means that it's the top paying jobs ever. And also you can see there's a news that the Meta super intelligence labs, they hire people where the salary is around 10 millions a year. It means for one people, they will pay 10 millions a year to ask them to do some research on deep learning. The second thing is that if you want to do some research, right now, deep learning is the right domain to do something. And it is the modern engine of research. Also, if you do not want to like really find a job in those domains, it is still an essential skills that you need to learn every day. Like it is just like email in the 1990s, and you have to learn this. And one of the challenge of learning the deep learning is that throughout those years, like it has around like 40 or 50 years history. There's too many techniques around deep learning. And if you can see it as a tree of these subjects, and there's so many roots under the earth. And what we see is something just above and those very popular things. And for the new beginner, it's quite hard to get an overall picture what deep learning is. So our solution is that we take a modern perspective. We just focus on post 2015, the 10 years ago techniques, and just ignore all the things before. But we will talk about some basics, but those are just basics for us, not the main focus of our course. And it gives us the freedom that we can learn a lot of new things and very exciting part. And then I will talk about some of the course logistics and details. Our course will take 13 weeks, including 12 lectures and 13 tutorials and 1 in-class midterm. And except to February 18th, it is the like holiday for lunar years. So everybody will go back home. And we will post all our materials on this Learn.Polyu. And all the slides will be available like within the same week the lecture goes. And our course structure will mainly go through 3 main pillars. The part 1 is modern training techniques. We need to know how we will train those models to build those models. The second thing is that the modern deep learning architectures. We need to know what those deep learning model looks like right now in our time to know how to design them. The third thing is quite important is that now everyone is using those generative deep learning models. So we need to go deeper into those techniques to build those generative deep learning models. And this is the schedule of our course. We will go from the basics of linear models to the end to some diffusion models that everyone is using right now to generate their images and large language model that behind those ChatGPT and DeepSeek. And except for like the February 18th, it is lunar New Year break. We are very lucky that all our other like holidays that does not occupy our time. So we can do all those lectures in person. So a little bit about myself. My name is Shi, and I'm a very new assistant professor in this PhD at AI. I did my PhD in NUS, and I spent some time in Oxford. And my research focus will most on like generative models and computer visions. And actually, my PhD thesis is on pure deep learning. Deep learning, how to design efficient and reusable deep learning architectures. And one more thing is that I'm always looking for students to do research. So if you have any questions or you are willing to do some research in related domains, feel free to send an email to me. And we have amazing TA teams. We have Chen Ming and Tang Long here. Like they can introduce themselves a little bit.
Okay. Hello everyone. I'm Cao Shimi, one of the teaching assistants of this class, and it's also my first time to be a TA. And I'm a PhD student in the Department of DSAI, and my research mainly focuses on evolutionary computation. And if you are interested in this research direction, feel free to contact me. I will introduce something to you. Thank you.
Hello everyone, my name is Shichang Long, and I'm also a PhD student from the Department of DSAI. My research focus is in the self-evolving memory of agents and large language models. And I'm very happy to be the TA of this course. And if you have any question, you can email me. Thank you.
Okay, thanks for those amazing TAs. They help a lot. And we also have the office hour on every Wednesday, still today, in the morning. If you have any questions, you can send email to our teaching team or join the Zoom sessions, or like just come to my office and I will try to answer like everything I know. And we will use some tools, most of them like interactive quizzes, and we'll do QAs in classes. And most importantly, we'll use the Learn at PolyU to post the course content, and also the email to exchange the questions and your ideas. And if you're, because the subject is quite new, and also like in all university, we can see that they have some deep learning courses. If you feel like there's a need to prepare some of the basic knowledge, you can go through those recommended courses from MIT or University of Toronto. They have very throughout explanation for the basics for deep learning. Also, there are some books, but one thing is that those books are quite old. It is something that like published like over 5 years ago. So sometimes the most modern topics and techniques, you can only get them through some research paper or blogs or videos. So it is highly recommended. You can go through the YouTube to see some of the latest techniques used in our course. And for the grading scheme, there are 4 main components. And we have 4 assignments. I will say very simple coding assignments. Like I intentionally make it simpler and to make sure the course is not overloaded. Also, I think very importantly, we have a course project with like 30% weights of the course. I think that's I will recommend everybody spend more time on the course projects. And we also have an in-class midterm exam and final exam. And why I designed this is that I want this deep learning course to be highly like practical focused, so that everyone can get a lot of hands-on ability into coding or project. And I know some of the students argue that this looks somehow overloaded. I will explain more later. So for the coding assignment, I will post it on every 2 weeks, and it also due within 2 weeks. And it is basically just I will hand out some Jupyter notebooks, and everyone fill in the functions and upload to the platform, and we will use some program to automatically grade those coding assignments. I will keep the assignment as lightweight as possible, such that each will take no longer than 1 hour. So you will not fear of those assignments. Those are quite simple assignments. Otherwise, our teaching team cannot handle so many submissions. And for the course projects, we want the students to build something cool. Like we'll have a group projects, and you guys can form a group on your own basis, and with 4 or 5 people, and doing some hands-on deep learning projects. And the topic's quite free. You can do anything you want, as long as it is related to deep learning models. For example, the video generation, image generation, you can do some agents for posting red notes. You can go deeper into the architecture, like design new attention patterns. And my suggestion is that you can start from week 1, that from now on, you can start to think about what project you want to do and what is the outcome of those projects. And you can form a group. And one more good thing is that if your project's quite good, we will consider to do a paper. I will try to push it to NIPS 2026. And the deadline is May, so that we have still, even after the course, we still have time to polish a paper. And before week 7, you guys can team up together, and at week 8, you can submit a proposal. Very short proposal is okay. Just describe what you will do. And the final thing you will submit is you need to submit a report. You need to submit a video recording of you guys presenting your projects. And quite importantly is that I want you guys to also keep it open source. It means that you need to upload it on GitHub. If you do not upload it on GitHub, I will not grade your project. And this course still has some prerequisites, like because you know that deep learning is quite built on top of mathematics and coding. And for mathematics, the most important thing is linear algebra and some probabilistic basics. Also for the coding, you need to have some basics in Python programming, and you need to know some basic machine learning algorithm or concepts like linear regression, like optimizations. But if you are not so familiar with some of those techniques or tools, you can just reach out to me. I will suggest you the right material to learn some of the basics. And for the course, the policy of our game is that because our class is about AI itself, I would highly recommend you guys to use AI tools to do the homework. But the important thing is that there has to be some boundaries in using these AI tools. You can use those AI tools to debugging, to explaining some of the concepts or polish your text, but it is not, you cannot just ask the AI tools to do all the homework for you, because most of them are coding assignments and projects. You have to say that the AI is your co-pilot, your captions. You cannot use AI to do all the things for you, because we will do double check and plagiarism check on our side. So please do not do plagiarisms or use those AI tools to do all your homework. Also, there's a late submission penalties that if you submit all those materials or assignments, 1 day will penalize for 10%. And after 3 days, there was no marks here. And please do not do parallel. And later we shift to our main focus, like some of the course content. Our subject name is called Modern Deep Learning. So I will divide my introduction to this subject into 3 parts, like introducing each of these keywords very specifically. What does learning means? Why does it mean deep? And why our course call it modern deep learning? First part is what is learning? Conventionally, if you are a computer science undergrad, you will learn to program. And program is this kind of thing that we write some programs and we have some design data, input data, and we feed those input and our handcrafted programs into the computer. It will give us the desired outputs. And the whole computer science or a lot of computer science theory is about how to guarantee this kind of code do exactly the same thing you want. But for machine learning, the whole pipeline is different. Machine learning means the machine learn the pattern of those programs from the data. You give the computer your input and output pairs, a large amount of input-output pairs, and it will automatically give you a program or code that you want to achieve this kind of desired behavior. And this is quite different from the classical algorithm or programming because the program itself is written by our machine. And deep learning is nothing but we store such kind of program into a neural network. So there is, we call a machine learning paradigm shift. Instead of writing a program like the machine learning, write a program that does the program from the data. So we learn a meta program that can help us to learn the program. So dive deeper into what this kind of pipeline is. How can we get this program on ourselves? First, we need to collect a lot of data for some input and desired output data. We feed input into the machine learning model itself. It will give us some predicted outputs. And we can compute the loss function between the prediction and our desired output. And it will give some value that measures how good or how bad our model is. And in return, we will feed those score into the optimization algorithm that you will update the parameter of the model such that it will give us a new model. And by iterating through these loops, we can get, eventually it will end up into a new model. Such model will give us the desired behavior for exactly the same as our data. If it gives the new input data n, it will give us the correct output. And based on the type of outputs we will use, we can categorize into three main types. First is unsupervised. If we learn the pattern from the data itself, we call it unsupervised learning. If we have some ground truth outputs, we can say it's a supervised learning. And if we do not have the exact outputs, but we have some rating for these outputs, we call it reinforcement learning. And this kind of rating for the output, we call it reward. And we can see the differences are quite small. It only depends on the form of data, the form of output you have. All they have input data, they fit into the model. If it has the desired outputs, it is supervised learning. If it has only the inputs, and we need to learn the model from the input data alone, it's called unsupervised learning. If we get the rating or the reward from the environment, how good the output is, it is called reinforcement learning. And this is a diagram that for unsupervised learning, we can learn certain kind of clustering of the data structure. For supervised learning, we have the label for the data so that we can do certain kind of classification from the crossing from the circles. Or from the reinforcement learning, we have some states that transit from one to another, and the output has some reward to guide the model to learn the desired pattern of doing those actions. And why people want to use this machine learning to do their thing? I think one very important thing is that typically if we want to create a program by human beings, the process is very complicated. You'll need to ask a large internet company to write a program for you to classify all the images all around the world. They will devote thousands of people, thousands of hours into coding this kind of program. And for those kind of tasks with extraordinary complexities, human program can hardly achieve this. The second thing is that the programming is written by human. It means that it is always restricted by the intelligence or performance of human beings. If we want to achieve something beyond human, and there needs to be some new algorithm that write the code for you. The third thing is the adaptabilities, that the system must adjust to the changing of the environment. If the environment changes, and you need to, if you do programming, you need to ask the human coder to rewrite the program for you, and it is a very slow process. But as long as you collect new data from this environment, the machine learning algorithm will help you to automatically to do this adaptation. The fourth thing is that the scales, because we can hardly have everyone as the algorithm designer. So if we want to personalize those programs for everyone, it is quite hard. So if we can collect some data, it is more practical to collect some data from each individuals. So we can use those collected small data to train this machine learning models. So we can personalize those models to each of the users. As long as we know what learning is, we go to what does the deep means. So in our course, what do we mean by deep? I think it's not about some thinking or learning process that humans do that we think very deep into the questions. Also in machine learning or in statistics, there are other terms that use the term of deep to describe their models, like deep forest, deep trees, deep graphical, probabilistic graphical models. But in our course, we use the term of deep learning to describe very specifically to learn machine learning with deep neural networks, but not other concepts. So what do those neural network means? I think you guys have learned similar ideas in other classes, and it is the same that we those machine learning scientists, they learn from how our human beings works, and they simplify the model of neurons into this kind of structures. There has some inputs, it goes through some channels, and the signal within the channels are magnified or like they scale down, and it gets some outputs. And the neural does this in a biological ways, but in machines we cannot do that. The only way we can do is that we have some weights within those channels, like within those connections, so that input values multiply by those weights and get our outputs. And also it was manipulated by some activation nonlinear functions, so that it is not a linear relation between the input and outputs. It can learn arbitrary linear like relation between the input and outputs. So we can see that those neural networks is very simple. It's a combination of many very simple processing units that perform this computation, this multiplication, addition with a nonlinear function. So why people trying to study neural networks? First, I think the most important one is that it is the only proof of concept that the physical system can have the ability to acquire intelligence. We, human beings, or other kind of animals, they all have these biological neurons, and by mimic this kind of neural structures, we can somehow wants to eventually build artificial neural network can mimic our intelligence. The second thing is that people try to use this, find that it's very useful in different applications. The third thing is that those neural networks, because in our human brains, they are distributed. And so it's highly compatible with current computer systems, so that we can use very powerful GPUs and software framework to build this system, and it runs surprisingly well on our current computing devices. As we know, there's the name of deep learning. We call it learning with deep neural network. And the deep refers to the number of layers within those networks. Why we should use those deep neural network instead of some shallow neural network, or a very fat but shallow network? And people find that there are some reasons, maybe not all of them are present in all network, but they find some clues that this works. The first thing is that with this deep neural networks, different layers, their hierarchy of features. It means that with the first layers, they learn some kind of abstraction of the raw data itself. And the second layer, it learns an abstraction of abstraction. And the third layer, it goes even more abstract, such that it is similar to how humans recognize the real world. The second thing is that it can do end-to-end learning. Previously, if we are doing some machine learning algorithms, we need to put those raw input, raw text, raw pixels, extract certain kind of statistic features from those input data, such as the mean value, the max value, or different kind of statistic representation of the data itself to input to our machine learning model, such that it can make good predictions. But using those deep neural networks, people find that no need to do those feature extraction or feature representations. All we need to do is to input those raw data into the model, and the backpropagation will solve all the questions for you. And raw input in, the correct output out. Let's see an example of how the deep learning model works and learn this kind of different abstractions. And the most important deep neural networks, I will say this is an example, AlexNet. It is the first time that in 2022 that deep convolutional neural networks beat human in recognize images of thousands of categories. And you can see it's quite simple. It's some convolutional layer followed by pooling layers and convolutional layers. And gradually it gets deeper, and the vector, the dimension of the vector becomes larger. And that is how simple it is. And instead of just training those models, people are trying to dive deeper into those models to see how those models learn those features. What does this vector look like? And they trying to like uncover or map those features back to the pixel space to see what information is encoded in each of the layers. And this is one of the results from the AlexNet. From the very first few layers, it only learns some local patterns like edges or textures. And as long as it goes deeper into the network, you can see some parts, some shapes, or the objects are gradually come more obvious. Like you can see some human eyes, some dog faces, or the legs of humans like present in the decoded features. So it supports our assumption that deep learning model learns more and more abstract concepts through the stacking of layers. Also, these representations are not just for visualization. They are very good at we represent the input data as a vectors. For example, this diagram shows an example that we put all those images into those deep neural networks, and by training those models, it can do surprisingly well because in the output it's just vectors of scalar numbers, and we can use those vectors as a representation of the status, and we can do certain kind of dimension reduction. We find that those vectors are locally clustered together for the similar object, like all the cats are clustered together, all the black cats are clustered together, all the red cats are clustered together, and dogs as well. So those representation can serve as very important, good semantic abstraction of the raw data itself. And another example for those representation is a very old school learning like NLP model called Watervet. Like by training those neural network at large scale to do unsupervised training, they can map the original text data into some high dimensional vectors. And here is a downsampled a view of those vectors. You can see that this is an example of those genders, that the same line connects two words of the same meaning but different genders, like for man and woman, and sir and madam, and king and queen. You can see that it all lies in certain kind of directions that point into the right upper direction of the diagram. So those semantic relationships are very accurately captured by this mathematical relationship between these vectors, so that later on people are trying to use this kind of vectorized numbers to represent the semantics. For example, if you have a king vector u minus a man vector plus a woman vector, it will give us a very close to a queen vector. And then we show some of the example of those supervised and unsupervised learning performed by deep neural networks. And the first ever, the simplest application of this neural network is to perform those 10-digit classification on this MNIST dataset. And it works like the firefly of neural network research. And using those neural networks, it achieves 99% accuracy in 1990s. And actually, the inventor of those neural networks then won the Turing Award, like the Yann LeCun. What they do is that they feed all those pixels into the neural networks. They have a label from 0 to 1 to 10 to 9, and they do supervised training to make them can predict the correct number for the handwriting digit. Also, this idea can be extended to large neural networks. Like I just mentioned, AlexNet, they beat human beings in 2018 and recognized thousands of categories of images. They has 1.2 million training data sets and 100K testing data sets. And it can achieve like above 90% accuracy in top 5% of the prediction. Except for classification, another very important application is called image captioning. Even nowadays, this application is widely used. If you put your selfie onto the ChatGPT, you ask, what does this image look like? Or how does this person look like? You will give natural language outputs to describe the scene. And the task is called captioning. Like in the old days, people trying to collect the pair of images and text data. They use some vision encoder to encode these images, and using some language generation models like the recurrent neural networks to generate word by word those language outputs. And this can be done in 2015. And also, one important supervised learning is called translations. It is still something we are using today. And people, those old school neural network researchers do those seconds to seconds models that they have this word as input to the recurrent neural networks, and they encode it as a hidden vectors and thus in this bottleneck, and then feed it into the decoder such that it can decode into the correct output as a translation of the input. As long as you collect a lot of pairs of those input and output translations, you can train this model. Except for supervised learning, we can also do unsupervised learning. Unsupervised learning means that we learn only from the data itself. A very important example is image generations. It means we only have images. We want to train the model to generate the images that we do not see before. This example is from 2014. It's using like generative adversarial networks. It means from a pure noise, you have a network to map it into the pixel space, such that you have a discriminator to see if this generated images is real or fake. That is the idea of generative adversarial networks. You can see, even if it's the best performance at that time, it's very blurry and cannot be used in everyday life. Even your grandma knows that it's fake. And till maybe this year or last year or like the 2 or 3 years, there has a new techniques called diffusion models. Diffusion models works in a similar idea that from a pure Gaussian noise, they want to train a model gradually, step by step, the noise to a clean and realistic raw images. And you can see those large companies, they have a lot of high resolution images, and so they can train those stable diffusion models, or the flux is another diffusion models. They do it surprisingly well that nowadays you cannot see any artifacts in those images. And of course, you can say that it is the image has never existed in human history because there's no images of a panda drinking in a bar. And one very important like unsupervised learning applications is we learn the representation. As we mentioned about, learning representation is I would say the core task of deep learning, because it has the ability to learn representation from the data. But other machine learning method cannot. Now people are trying to use the self-supervised learning method to train a good representation of this vision inputs. Self-supervised, this method as in working this way, they have the same images, they crop it or rotate it and put the two versions of the same image into the neural network, and it extracts some high-level representations. And the neural network wants to do this thing. They want to cluster the images of the same, the different version of the same images closer, but this images is far away from another image. So by performing this kind of so-called contrastive learning or pairwise corresponding, like the similarity learning, the model can represent the image quite precisely. And they visualize some of the features at higher level. You can see that, for example, it can correspond the wings of the birds to the wings of the airplanes, but it has never seen any labels as wings or something like that. And even for different kind of object or creatures, or they have certain kind of clustering ability that associate different part of the classes all together, even if they didn't see them and train. I think one of the most important unsupervised learning example today is what we call language model. And language model means that we train a the neural network, the input language, and they can extract feature from those languages without human annotated labels. And they just download, for example, those GPT or DeepSeek or Llama or Claude, they all download all the resources they have online. And they train a model to make the mask word prediction. They mask part of the sentence and use a neural network to generate the missing part. And then we do not have any human labels. All we have is a large amount of corpus. And the model wants to fill in the blanks. And this idea works surprisingly well. Those large language models are trying to scale it up to like trillions of tokens and with a tremendously large neural network. And it is the most like popular deep learning models all around the world, including human history. And the last example is reinforcement learning. Reinforcement learning using deep neural network is also quite popular because nowadays people are trying to use those reinforcement learning algorithms to retrain those large language model to perform the task we want it to perform. It means that, for example, we assume those agent it is a language model, and their action is they want to try to output some of the description to go through the maze, but until it reaches the end, the output the exit of the maze, it can never know it is good or bad, so that it can only give you a certain kind of reward. It's closer to the maze, the exit of the maze, or not. Other than they do not have their ground truth trajectory for those maze working. By giving those reward, they can give those reward back to the agents such that they maximize this kind of reward. And by iterating through those simulation, reward, and retraining process, and we have better agents. And these are widely used in a lot of robotics or nowadays those reasoning language model applications. Finally, we will go through why we call this course model. Because there are, you can see that in every university, there are some courses called deep learning, deep neural networks, learning with deep neural networks, something like that. But those traditional deep learning courses, they will focus on very simplistic examples like handcrafted architectures and toy example like MNIST. And they spend a lot of time introducing those optimization algorithms with very old school architectures. But within our course, we want to step a little bit further. We will focus more on the systematic integration of those deep learning models and use some off-the-shelf tools. We are not trying to build small neural networks from scratch. We want to use all those tools we have available on the internet to build more advanced models. And we will use more real-world data set and multimodal data sets. And we will do a lot of large scale. We will introduce how to do those large scale distributed training. Although we do not have resources, we need to know how this is done. And we will introduce a lot of those large language model, how it works, the diffusion models, how to perform some those graph neural networks. And we will use some tools like Hugging Faces or more advanced open source models. First is our training techniques. We want to go beyond those back propagations. Like for typical deep learning courses, they will stop at the first point. Like we do back propagation, that's it. That's the end of the story. But we want to go a little bit further onto how to do also differentiation, how to train this model across different GPUs, and how to optimize those models more stably with larger neural nets, how to improve their generalization and using better optimization algorithms, and how to make sure they run efficiently on model GPUs. The second thing is the architecture. Architecture means how those neurons are organized together. Typically, they will end certain kind of transformers, the introduction of attention, that's it. And we will go slightly deeper, like modern, like convolutional neural networks, how that looks like, and how does modern sequence modeling perform, like those attention models replace those recurrent neural networks. Also, there are new state space models or linear attentions that performs long context neural net like sequence processing. How does they work and why we need them? Also, we will introduce transformers and its core mechanism called self-attention or attention. Also, we will introduce the mixture of expert. It is the architecture of those DeepSeek models. We will actually use. It is a more efficient architecture for those language models. Also, we will introduce some of the ideas of graph neural networks and also graph transformers. And the third one is that we will introduce some of the generative AI like models, and we will go through some of the foundations, like why they call it generative model, because they build a model to model the distribution of those samples. Like we will see how those models are mathematically formalized. Also, we will introduce like language generation, image generation with diffusion models, and and we'll give some examples on how those video models or 3D generation models are used. And the last pieces is that we want to focus more on the modern toolkit of the deep learning. Instead of building like models from scratch using Python or NumPy, we will go upper level and using from except the language part, we will use more framework-wise tools like PyTorch, Lightning, or you will name other kind of framework that you can build application more easily. And even more important, nowadays people train deep neural networks. They just download their open source models in the platform like Hugging Face, TIMM, or diffusers, and they just run on their computers. So we will introduce how to use them or use those ecosystem or off-the-shelf tools to build your own applications. And that's the end of first section. I have a quick rule to know more about your guys' background, because I would say this is a more technical course, and because I do not know your background, I do not know how much technical detail I will dive in, and I have a small and also this we can start like 5 minutes break, and you guys can go to the restroom if you want, and 5 minutes later we can come back to start our next session on introducing the linear models. We will like in 37. Okay, thank you.
你这个 PDF 用那个 Preview 打开应该就能。
OK，可以，再这样，我先把那个东西，我先把。
你现在都是这样空着讲。
对，
我看老师一直沿着。
哎，对呀，我怎么一直空着？主要他没给我时间就这样，我前面那个90好玩，是吧？有到这个时间。
霍老师，你要不先开启那个屏幕镜像，这样的话在笔记本上也能。
哎，对，怎么开启那个？
我看我是直接这张，
在右上角的。
If you guys have time, you can like scan the QR code and fill some of those questions. There are 3 questions you can see, like I need those information to understand more of your background on the subject. Thank you.
你看按这个 F3应该快捷键吗？不是这个，那就直接找设置吧，系统设置。
这个啊，system setting。
系统 setting，我看我那个是在这儿的，这个哦
OK。哦，OK mirror screen OK。X好 display setting。刚刚那个好像有 screen。哎呀，差不多。Stage manager change。OK extend entire screen。
你这样会把整个就 copy 过去。
mirror。
OK
对了，
这就对了。哎呀，差点死了，我去。OK，行，感谢。
还有那老师那个 PDF 的全屏
哦，对
，PDF 就是我看用那个 preview。
这个我应该知道怎么去评。
好嘞。那老师，那我们就
你们可以先溜了。
好，
行。
I'm a year two student.
Okay.
I'm interested in your internship, and this is my CV.
You can send me.
I send me
Oh,
an email. Change my CV.
Okay.
Change it because maybe that version is not so attractive. and
Your
not-
undergrad that.
Yeah, I'm interested in your research internship here. And
Let me see. What kind of project have you done?
actually, I'm now a student research assistant in the SAI department. One of the
With
with Professor Yang.
which professor? Yang Chang or Yang?
Yang Hu.
Okay, Yang. Okay.
Yeah. Sorry.
You're doing for the reason. Okay. I think I see a good match, and you have great experience.
Yeah.
What project are you doing right now?
So that project is about the model to learn about the real world physical principle.
For example, what kind of
Gravity and things like that.
do you have data? Because
It's in my disk.
Okay.
And
we can chat later. Like I need to do the lecture, but I think I see a good match. Because that's one topic I want to do, like to infer the physics from the videos or images, like the gravity or materials. So that.
Yeah, and I'm also learning something about the generative AI because I'm just an undergraduate, so I just want to explore more about it.
Okay. So if you have time later this week, you
Yeah,
can talk,
okay.
or you can. I think it's quite hard to have you here waiting for the end of the lecture. But if you have time
Oh,
later this. Okay. Thank you.
So I will email you.
Okay, no problem. Okay. Like there are 3 questions. This is the second question. Like you need to like input your like undergrad subject. So like I know more of your background. So to design this courses. Thank you.
The survey, just now I'm maybe in level 4.
Okay.
Yeah.
Okay. I see.
I realize
Even if you're in second year, you started doing research.
so I want to pursue the PhD in the future. So I want to take part in participating some research now.
Okay.
Yeah.
It's quite nice because I have some undergrad, especially I see the girls in Poly, you are quite capable because I have some undergrads in comm department. They
Maybe I heard of it.
Oh, okay.
Maybe.
It's she introduced you to me, like because they're very capable because I know her from July, and then
Oh,
you can do a paper with me like within half a year. So that's quite big. I think it's the first paper he do.
I think maybe she is famous in Hollywood.
Why?
Because I know her. Maybe we talk about the same person.
Okay, so-
And I know her from her 小红书.
Oh, I see. I see.
Yeah.
Okay. Maybe we talk later this. Okay. Hello.
I use Chinese too，
可以。
就是我们是这样子的，就是我是那个就是3人学派的 analytics 的那个学生，然后我们那个 project 的话，program 的话是可以写论文，
可以有个 dissertation 我看到。
对，写论文还抵那个3节课的学分的。
OK。
然后我想在写论文之前，因为他是要求第2学期结束之后才开始这个工作，然后我想在写论文之前先进行一些训练。
OK。
不知道老师您这儿有没有？
可以的吧？但你确定要做这个？你 long term 你是想干什么？是找工作还是想读还是想？
现在就是还没有很确定，所以先想，
你可以给我发个邮件吧，你说你
好
想做这个，然后
嗯。
大概你自己之前做过什么
之前就是在读书前面1年，有做过1年的那个科研助理
OK
在我本科的指导师那里。
？OK。
然后一开始是帮一个博士师姐帮他去完成他多模态的那个 computer precision 那一块儿，后面他不太需要这一块了，我就变成单独做了一些别的
OK
事。嗯，
你可以给我发个邮件吗？
可以。
好。
那如果是工作的话，是您来定方向对不对？
应该是吧？你定的方让
我应该
定方向
会把定方向。
对
好，谢谢。
谢谢。
嗯。
And we also have the third questions, like what's your hope to gain from these courses? Like you can fill the last questions all together, like and maybe we will start at like 41. Please. Okay, we can see some of the results here, like I think we have a nearly uniform or a little bit a wide Gaussian distribution for the understanding of those deep learning techniques. Like very few are never heard of it. Also, very few have heavy experience in those techniques. And most of you have heard some basic terms, but and understand the basic concept, but not quite fully familiar with this. Also, most of your background is in computer science, but there are still some backgrounds in physics, applied mathematics, statistics, and software engineering. And I need to balance a little bit on the technical details I will introduce. And I think most of you want to have hand-on coding skills and to train those models, to understand those models. And I will be a little bit surprised because I will say a lot of people want to find a job, so they are trying to learn the courses to get prepared for some interview questions or to find jobs. But okay, I see. So we can start our second half for linear models. Okay. Okay, we can start our second part. We will introduce the most fundamental deep learning, maybe not deep, but neural network model called linear model. It's actually not so-called a neural net. It's a conventional like machine learning algorithm, but it is the basics of neural networks, and it will involve a lot of things on linear algebra. So I put a lot of equation in it, and I will explain it step by step. If you have any questions, feel free to ask. So those linear the very beginning of the story is that we're trying to build a deep learning models, but each layer of it is linear functions. So each layer, it's the input vector is multiplied by a matrix plus a bias. You can if you ignore the nonlinear functions, it is called, if it's a nonlinear function is a linear functions or identity functions, it is a linear model. And in this small lecture, I will review the linear models and some of the foundational concepts, and how to train those models, how to do regression, how to do classifications, and so on and so forth. This part will divide into three small components. First is linear regression. The problem set up is we have a lot of data points. They have some inputs in the x-axis and some desired outputs on the y-axis. You can think of this as stock price or the height of each person in this classroom. And we want to train a model to make a prediction for future input values. A linear model looks like this. The input and output, we assume it to follow a linear relationship. It has an input multiplied by a matrix and plus some bias. And the y is the prediction. And the matrix and the bias are the weights of the models. And if you, even in your primary schools, you will learn there's a slope in the functions or the bias for the functions. And learning this kind of model, you can see that it as searching for the best weights and bias. And on the left-hand side, from the data space, the left-hand side is a data space. We feed the linear models. And every linear model we feed can be mapped to a weight space. And the one line in the data space corresponds to 1 point in the weight space. You can see this as find the best curve, the best straight line, or find the best points in the weight space that make the best prediction given our data set. And we need to define certain kind of objective to find a good. What does we mean by good solutions? So we will need to define some loss functions. For the simplistic case, we will use square loss or L2 loss. It means that every time we make a prediction, y, we will minus with the target and get the square divided by 2. And this y minus t is called the residual. And the divided by 2 makes the derivative. Like if you take a derivative of a square, the 2 comes in front of the term. And if you divide by 2, you will make the derivative always stable. And for single sample, it looks like this. But for entire data sets, for n different samples, we can have a cost function. That means we take an average of all the single loss function of each individual samples and average them all together. That's it. And and this cost function, they somehow becomes a quadratic function of the W and the weights and the bias. And it somehow forms certain kind of surface of the cost functions correspond to the selection of the bias and weights. For example, on the right-hand side, you can see it's a quadratic function. We look at the quadratic function from above. Like we're standing at the top of a mountain looking downside, there was a quadratic function. And there's the shape of the quadratic function in here. And different points on this surface means the weight, as we just introduced, in the weight space, each solution corresponds to a point. And these different points correspond to different lines within the data space. And different solutions have different errors. You can see that the red curve, red line, like maybe gives you the best fit for the data, so that the red dots in the error space or the cost surface give you the lowest cost. And instead of doing all this in a for loop that we just minimize the loss function for each individual samples, we need to use linear algebra to combine them all together in a matrix form. For example, we can stack all the sample together into a bold X matrix. also the targets can also be stacked together into a n-dimensional matrix, the vectors. And for example, here is we stacking different samples together, and each row like represent one training example, and each columns represent one feature from the training examples. And our batch prediction can look like this. It's still looks like a matrix multiplication plus the bias. And the bold one means that we have a column of ones, but they are stacking together. So we mark it as bold. So if you want to give a mathematical notations in a matrix form, you still a matrix of examples multiplied by the weights and plus a bias. And the cost function is that in the vector form, that you have the y as a vector, you have the subtraction of the vectors, and you take the L2 norm of the vectors. And this is a Python implementation of the problem itself. And the most important problem, not only in linear models, but also for all deep learning problem, is we want to find the best solution or the best weight matrix such that it minimizes our cost function. And this can go back to an optimization problem such that we find solution gives the least the least cost. And from the if you have ever taken the calculus classes, you will know that solving this kind of optimization is quite simple. You will given this cost, you take the partial derivative and set it to 0, and the points, all those points, that's the weights, all those solutions that gives 0 derivative can possibly be n solutions. And all of them are called critical points, but critical points are not all solutions. Some of them are, some of them are not. And in this part, we will describe two kind of strategy to solve those questions. The first is we just use the principle of partial the derivatives to get a closed form solutions, and you can solve the system of a linear equation directly, and it will always give you an optimal solution. The second one is an iterative method. Like we're starting from a one weight, an initial weight, and we gradually go down hills. Like we start from those green points, and we want to gradually step towards the minimum of the cost service. And that is gradient descent. And gradient descent is the concept we'll always be using through our entire course. And it is the universal method of deep learning. First, we will introduce the direct solutions. So that is the formulation of that we just introduced above. And that's the cost function in the matrix form. And if because it's a quadratic function, it is a convex optimization problem. And the optimal solution, they only have one critical point. And the optimal solution must satisfy that all those partial derivatives equals 0. And we will see later how to use this partial this equation to solve the problem. And for example, for per example, it has a loss and the prediction. And for the chain rule, we have the cost for each individual examples. We want to take the partial derivative of the cost function or to the weights, and it can be expanded into a chain of derivatives. Like first one is the loss function has some relation to the output of the linear model. Then the second term means that the output of the models have relation to the weights of the linear functions. And for the first one, it's quite simple, like it's just a derivative of the square function. And we put the 2 at the front, and then it becomes y minus t. And for the second one, the derivative from y to w means that it means the b does not involve in any computation with w. The only thing that involves is x. The input example multiply with the matrix and gives you output. Because it's a linear function, the derivative is x itself. So then we get the derivative for the partial derivative for our w. Also, the same apply for b. The loss function take derivative, like the loss function take derivative to this will equal to y plus t, y minus t, and because for b it has only the coefficient of 1, so that it also have a derivative of 1. So then it will gives the derivative like this. And by over all the data sets, you can give a matrix form of this partial derivatives like this. You can see that it's completely the same. Instead, but it's just a matrix form for the bias and for the weight. So the problem is that we want to set the gradient to 0. That's quite simple. Like if we expand the y into like into this form, and we have these two equations. So because those kind of one looks quite the bias and the weights looks quite strange in this way. We just augment the system, just plus 1 columns to the original x to make it the x tilde, to add 1 dimension. The dimension is the multiplier of bias. Also, we put the weights and the bias into a single vectors, and we have y equals x tilde, w tilde. And in that form, we can, from this one to, let me write it down. X transpose x, because the bias and x tilde, w tilde minus t equals 0. Also the same for the second one. It means that we have the x tilde w tilde minus t. It's at the boundary. Minus t that equals 0. And if we put these two together, we can have xt, we can extract the same term here, like x tilde w tilde minus t equals 0. But this becomes the x. You can change this x into x tilde because it combines those two together. Let me, like, you can erase this out. But it is a transpose because in the beginning it's a transpose. Then we have this kind of equation. It's exactly the same. You multiply it into the term. You have the x tilde transpose x tilde w equals x tilde transpose t. And if you want to solve for the best w, and you can, if this gives you a normal equations, and it's a linear equations, that if you want to solve for those variables, you need to take the inversion of those x tilde transpose x tilde. And if that's invertible, That's still a question, not sure. For every linear system, that's a variable, not sure. But if it is an invertible matrix, and we can invert it, and we can give the best matrix, best weights to feed the data. The good thing here is that although we go through all along the way, it looks quite complicated. In the end, it's just give you a closed form solution. Okay, given your data and your the input data and your output labeled outputs, it gives you a solution of the weights such that it best represent the data that minimize the square loss. It is exact solution. There's no hyperparameters, and it's known as the optimal solution for this kind of problem. But the problem is that this kind of matrix multiplication is multiplication and inversion is extremely expensive. If you have an image of thousands of dimensions, this inversion is something extremely tedious and very slow for large dimensions. The second solution is what we call gradient descent. And instead of directly compute the inversion of the matrix, we can iteratively adjust the weights in the direction that goes to the optimal of the solution. First, we can have initial weights. No matter how random it is, we are somewhere on the cost surface. Any place, that's good. But later on, we'll go gradually towards the best solution. Yes, and we can repeatedly update the weights such that it go through the derivative of the cost surface from like at other points of the weights. There was the slope go along the slope that go deepest along the direction of the gradient, and all through the data sets we have this kind of representation. That's the thing we have already calculated above, like this one. We already calculate the derivative of the loss with respect to the weights, and we go through the trajectory. There was a step size and the control, how much we go through along the directions, and that's how we solve this kind of questions. We iteratively do that, and in a matrix form, it will look like this. We concatenate all those individual value of the gradients together to give a vector of the gradients, and in the direction of the gradients, we iteratively go along the directions, and in the end, we will go to the solution of the problem. And the good thing is that there's no need to do this kind of matrix multiplications or inversion anymore. All we need to do is to compute the local gradients and step by step go along the trajectory. And it's somehow very close to how human learns. So we do not know the overall situation. Every time we just look around this the environment around us and do the solution that currently seems to reach the final goal. And why do this gradient descent idea very popular? Because the direct solution gives us the optimal case. Why this gradient descent still works? I think there are three different reasons. The first is it's quite scalable. Scalable means that if we have large matrix or large amount of data, if we do the matrix inversion above, it's quite expensive. But for gradient descent, every time it's only need to compute the gradient, and the complexity is much smaller. The second thing is that the gradient descent is much more generalizable, because now the problem is a convex problem. It means that it has unique solutions, and all those maybe lacks next week's lecture we'll cover what does convex problem means. But now we just see that today's question is a quadratic function that is quite simple. We can have a closed form solution here, but if the problem goes much more complex, for example, we do not have linear models, we have nonlinear models, we have nonlinear optimization problems, then the direct solution becomes not viable. And only the gradient descent can works because it's no matter how large or how complex the model is, we can always go through the chain rules to some of the parameters to update it. The third thing is that it is quite simple to implement because you do not need to go through all those mathematical derivations to compute the optimal solutions. All we need to do is to compute the gradient. And then every time we take one step, that's it. Besides to have linear models, sometimes the assumption fails. It's the relation between the input and output is not linear. It's not look like a straight line. So we need to create some kind of non-linear function or non-linear mapping to extract some higher order feature from the data itself. So that's a term we will call feature mapping or feature extractions. We can create some nonlinear features from the data itself. For example, we can have a polynomial regression, like given some raw inputs, we can have some like higher order components and concatenate them into a vector. And in that way, why we just assume the output is a polynomial of the inputs itself. And we can solve the polynomial regression exactly the same as a linear regression, except the input becomes a polynomial of the inputs. But the ways we optimize the W is the same. But here, the hardest part is how we choose the right feature mapping or the order of features here. For example, if we only have first 0 orders, it means we have a flat line. It can never fit the data itself. It have a first order, it's still linear models. We can still not feed the data. If we have a third order polynomial, it somehow feed the data quite smoothly. But if we have even larger orders, like the ninth orders, it somehow gives very like cracky curves that does not feed the data exactly good, but does not capture the smooth trend of the data. And this connects to the concept of complexity and generalization in machine learning. If we choose a too simple model and it cannot fit the data well, we call it underfitting. Because the data model is too simple, it can, no matter what the solution you look, it cannot never fit the data well. It can always have a large testing error. If we go beyond the current training data, you will assume it follows certain kind of cosine or sine patterns. It can never fit the data. And the good model should look like this. It fits the data at just the right complexity. It has small testing errors, and it can somehow generalize well to the data we do not see. And for the outfitting, it means that we have a too complex model. It fits the training data perfectly, but it can hardly generalize to the data that's not seen. For example, here. And the core problem of machine learning is to find a model that can generalize. Because no matter how much training data we have, all we want to test is something we do not see in our life. And we want the model to generalize to the thing we do not see. And the degree of those polynomials or the complexity of the models itself is an example of what we call hyperparameters. Or in the rest of the course, there's different hyperparameters like the architecture of the models, the size of the models, the different kind of, and they defines the complexity of the model itself. And if you choose the model that is super complex or super simple, it can never gives you a good generalization performance. And we can somehow tune those hyperparameters using a validation set. Like given that we have a data, we can divide it into a training set that we see, a validation set that we do internal testing, that we train model on training set, and we try to report the performance on the validation set. And in the end, we do real testing on the test set that we do not see before. And besides regressions, there's another whole part of machine learning is called classification. And we will introduce some of the basic classification models. Also has very close relationship with the linear model. For example, we want to do a binary classification. It's quite simple. We want a model to predict the target. It's either 0 or 1. And the one is we have positive classes, like we have the example diagnosis with certain kind of diseases, also negative predictions that is quite useful. And the very simple idea is to have a linear model with threshold. And it's the first real neural network. It's called perceptron. And we compute a linear score, or we call it logit. Later on, we'll know why we call it logit. And we apply a hard threshold. We have a linear function of an input, and if it's above 0, the output is above 0, we know it's positive. It's below 0, it's negative. And this kind of model is called perceptron. You can see that it is a simple model with linear function, and its outputs is defined by a threshold. The problem of this kind of classification, binary classification model, is that we cannot compute the gradient. And above, we show that if we want to solve the questions, the most important factor is that we want to compute the gradients for the error in respect to the weights. Now, for this kind of model, we cannot use gradient descent because the hard threshold function, or we call step function, is discontinuous at the points of threshold. Like at that point, we always have this. It has this kind of, the hard threshold function always look like this. At the point of 0, there is no derivative, but at the other part, there is the derivatives is always is still, the gradient is 0 for all the domains except for this one. There is no definition of derivative at the point of 0. So the weights can never be updated because we cannot compute the gradients. So the solution is that instead of having a completely hard threshold functions, we can do certain kind of soft classification. Instead of output 0 or 1, we can predict a continuous value such that it defines the probability that the target is 1 given x. It allows us to give a smoother or differentiable loss function. Here gives the concept of logistic regressions or a sigmoid functions. So instead of using a hard threshold, we use a soft threshold. The soft threshold means that around the point of zeros, it's around 0.5, and then it goes quickly into 1, into completely positive. Or it goes to the negative side, goes to completely 0 into negative. And this kind of S-shape or sigmoid functions looks like this. And then we can have a log linear models that its output is still a linear function, but its output is mapped through a sigmoid function. And to train such kind of model, we cannot just use the loss we introduced above, like the L2 loss, because now the outputs represent certain kind of probability. And if we interpret this kind of output as the estimated probability of output target is positive, and we need some kind of losses that optimize this kind of probability. And L2 loss is not the case. People use this kind of cross entropy loss. Why they call it entropy? Because this kind of thing, they use this kind of term to measure the uncertainty. And in information theory, this kind of uncertainty is called entropy. We want to minimize the kind of uncertainty we give the predictions. And for binary classification, the entropy will look like this. It's a binary entropy. It somehow defines the entropy for positive samples and negative samples. If it is positive samples, then only the first term will remain here. Because if it's if t equals 1, then this equals 0. It can completely cancel out. And if the target is negative and only the second term preserve, the first term also cancel out. And in this way, we will by optimizing this kind of cross entropy, we are actually minimize the uncertainty that it gives the right predictions. So we give the full pipeline, given the input, we go through a linear functions, and then we use a sigmoid function to convert it into certain kind of probability. And we compute the cross entropy to give you loss functions. And this kind of, then we will introduce how to backprop, compute the gradient of the loss function towards the weights itself, so we can perform the optimizations. And this kind of logistic or sigmoid function plus cross entropy gives a very good balance. Why they should become in this way? Because if the z value is because the loss follows this kind of curve, that if the error is very large, it almost follow a linear relationship. But if it goes small, it still has certain kind of uncertainty here, but it's quite small. So it will penalize the wrong predictions very large. But for the almost correct predictions, it will penalize less. So how to compute the gradient in such kind of formulations? It is still the same. We need to compute the gradient with respect to the output of the linear models. Then we will compute the gradient of the output of models with the weight. So let's just write it down again. The loss function is defined as binary cross entropy. Let me see it. Let me see it one more time. Okay, it's in this form. I do it here. This might look quite tedious, but I think that's the way we learn this very basics of very fundamental ideas of logistic regressions. And now we want to take the derivative of the loss function with respect to y. And for the log function, if you have take college calculus class, you will know that the log y, its derivative is y 1 divided by y, and with all its like terms in the beginning. And that's the first time. If we take the derivative, it looks like this. Also, it's the same for the second term, and the minus still here, and the scalar in the front, we still put it in the denominators, and the derivative for the log 1 minus y respect to y, it should be still 1 minus y, but there was a minus in front of y. So this should become plus. So if I do this together, it will end up like something like this, and then it gives the derivative of the gradient with respect to the y, the output of the sigmoid functions. Then the derivative of the sigmoid function is also quite simple. Like this is the form of sigmoid functions, and we can also do the derivative here. If like you can do this as homework, because we are kind of running out of time. I will not do that here, but if you do the derivative, you will see that the final output looks like this: y times 1 minus y, and put these two together, like the chain rules. The first term equals this, the second term equals this, and you multiply them together. It gives you a very beautiful solution. The gradient is just the prediction error, or the gradient itself is just the residual noise. And we need to update the backprop, the error signal, all into the weight again. And because because its derivative with respect to z is this, and z is a linear function, again, a linear function of x. So the derivative of z with respect to w is x, with respect to b is 1. So it somehow works here. So the final loss, the final gradient of the loss function, the cross entropy loss function with respect to the bias and the w, ends up in this form. And then we just goes the same thing. We use gradient descent for the initial weights. We do go along the direction of the gradients to update the weights with respect to some of the step size. And this update rule looks quite intuitive, because if we predict like the sample is positive, but the target is negative, and the term should narrow down the gap between those two. So we just use this error signals to update the weight matrix, to lower the score of such that you also lower the score of y. And that's, although it looks quite tedious, I would like to just re-emphasize it's just this form, a linear function followed by sigmoid functions, and the loss, we compute the cross entropy loss, and the cross entropy loss, you can compute its derivative with respect to the parameters of the linear models, and it will eventually end up in this way, and we do gradient descent. And this same idea can be extended to multi-class classification problem. It's still quite straightforward, in binary classification, we only have 0, 1, and 2 classes, and we need the model to perform more complicated classifications with category more than 2. For example, the hand digit classifications has 10 categories, the ImageNet has 1000 categories, and so on and so forth. And we need one representation to represent the ground truth target. And we use the one hot vector to do this kind of encoding. If one example belongs to the T class, and we have that position equals 1, and all other position equals 0. And only the T's entry is 1 if the sample belongs to that class. And this treat all classes independent and using a scalar. And if it's a binary classification, we can still think of it as that way. 1 is 0, 1 is if it belongs to the first class, looks like this. If it belongs to the second class, it looks like this. And it's generalized to the binary case. And still, we can have a linear models. It is completely the same. We have an input, but the output has k different linear classifiers, like k outputs. Like for the binary classification, we only have one output, but for the multi-class, we have multiple outputs. Like there's 3 classes. And instead of using the sigmoid functions, and we now use a softmax function because we do not want to choose, we just want to choose the one logit, one outputs that has the maximum probability such that it is the prediction of the model itself. It is called the same as the one hot encoding. The maximum one like gives all the credit. Instead of using the hard threshold or just using hard max, we use a softmax function. It looks very much similar to the sigmoid function above, and because all the exponential term bigger than 0, so the outputs are always positive, and each individual value means the probability that the sample belongs to that category. Also, it is normalized such that each probability is always in the range of 0 and 1. And it somehow amplifies the largest one and suppress other ones because you use an exponential term. If it's large enough, because exponential looks in this form. And if it's the output logic is large enough, it will dominate the scales. But if it's small enough, it will be canceled out quite easy. So we can see as a winner takes all behavior, that it fits the output is large enough, and it will gives almost closer to 1. The same thing happened here. We have a multi-class cross entropy or categorical cross entropy here. Like it's almost the same as a binary case, but for each category, because it's either 0 and 1, we sum all those loss together for each category, and it gives a cross entropy in this form. And it's also generalized to the binary case, because in binary case, you either have 1 or 0. If you have 1, you have one term cancel out, you only leave another one. So for this categorical, because we have one hot encoding, so that it only has one term for the one that belongs to the kth class, only that term is non-zero. For the rest of the term, it's 0. So it's quite simple if we use one hot like encoding. Only one term remain here. We only care about the probability to assign to the correct class. And for other like wrong predictions, we do not care. And the arrow, the backward propagation is eventually the same. And because the previous sigmoid functions generalized to here, through some very complicated derivations, we can see that the gradient of the loss cost entropy with respect to the output of the linear model is again looks like this, but it is in the vectorized form. And this is the raw prediction errors of the linear model. If the prediction is exactly, the intuition is that if the prediction is exactly the same as the target, the gradient is quite small or nearly zero, so there's no update. But if it's far from the target, the gradient is quite large. So we used the same notation, just backprop the take the gradient of the cross entropy with respect to the bias and the weights. It follows nearly the same formulation, except it's a vector form. And we can see that even though it looks quite complicated for the linear model, for softmax, we compute and the cross entropy and take the gradients, but it ends up to be quite very simple model of all. And I think that's all of the content for the second part. And I just recap a little bit. So I think this is a good intuitions of what we're doing all along the ways. Like we want to, given certain kind of loss function, given certain kind of models, we are trying to find a good solution. And that solution best fit the data. And the solution and the weight space is somehow correspond to a high dimensional curve. And the surface, we want to take gradients and go along the direction of the gradients to find the best solution. No matter it's a linear models, it is a sigma like logistic regression or like like classification with softmax for multi-class classifications. It all does the same thing. The only different thing is that they use slightly different loss functions, slightly different formulation of the gradients, but the solution, how we solve those questions, are completely the same. Okay, I think that's the end of my second section, and maybe we'll come back in like in 8:40 to conclude the last part. I think it's most valuable part because it's the part that I show you how to do your homework, do your assignments, and how to submit them in our system. Okay, thank you. Let me do this. Because I have designed a different and you don't want to. So there's the determine the person history. Yes. In just a bit, I don't know because we have foster I think it's better coding without much tool. That's everything. Because it's already having coding most of them. More concept in that just now. That's what I'm. Yeah, so And I'm going to start the last part, like the tutorial. Like it's most about how to how those assignment looks like and how to submit them. And I put a tutorial files in the Learn@PolyU. It's a sample, like I will say it's a sample assignment, and you can download it, and it will look like something like this. It should contain 2 files, because this time I also upload the answers to the questions as well to online. But for the assignment, it only will contain 1 Jupyter Notebook, look like this. And if you know what Jupyter Notebook is it's a script that contain all Python code and other things and description all together. And there are some suggestions for you how to do run this. Like you can directly open your Jupyter Notebook in command lines, and you can use your browser to coding. Or I typically use the Visual Studio Code and install the environment here, and you can run the Jupyter Notebook as well. Or if your laptop is not so powerful, I will recommend to use the Colab. Colab as well, it still can do its environment to run your Jupyter Notebook. It also provides some it still provides some functions for Jupyter Notebooks, and you can actually update the Jupyter Notebooks and run your script here. But today, in order to introduce how those works, I will just use the browser version of Jupyter Notebook, because I think that's slightly clear to demonstrate in the screen. And it will look like this, and please do not revise any of the format of those script. And later on, if you get your assignment, it look the same, because we will use some tools to automatically grade your homework without any human reviewer. So it's so the format is quite important. And we have some environments, some packages, and it's a demo of sample assignment, helps us to see what is going on, what to do. And this lecture we just learned what is linear regression and what is logistic regressions. And this sample coding demos gives us how to do that in code in Jupyter Notebook. And every time I will put some blanks here, and you will fill in those blanks by writing Python code. And we will for each assignment, I will have 5 or 10 functions you will put in, and each I think can be finished within 10 lines of code. And you can put your code here, and this will be automatically graded by a script. And so please do not revise any of the modify the tests or modify the function names or arguments. Do not delete any cells or change structure notebook. So that's a fixed structure Jupyter Notebooks, and only thing you do is just to put your code in here and submit online. And you need to change the file name to match your student ID. For example, if it's assignment 1 and your student ID is something like this, you just put it in this form. And later on, we also automatically pass the student ID from the file name. So if you put your student ID into someone else, your assignment will belong to someone else. So you upload the rename, you finish your assignment, and update the Jupyter Notebook onto assignment. They will I will post when it's ready, and you can submit and you'll upload your assignments here, and we can collect it on our end. And by collecting all the files, we will grade them and we'll upload the gradings onto the platform. And that's how we do those assignments are designed. And so you can see it's quite simple, and all through those, even if you go through all those questions, you can write less than like 15 lines of code. So I think pretty much sure you can finish it within like 1 hour if you are familiar with Python and all those environments. So I will try to solve some of the questions by myself. Like first one is a linear regression, the most basic model we just introduced right now. Like for first one is we need to implement a forward pass for the linear model. For example, we assume that x, w, and b are all NumPy array. It's in Python, it's data structure to store the matrix or vectors in NumPy. For example, I can return x matrix multiplication w plus by b, and I import all the environments, and I can run this cell, and the grader function will check if that works. Okay, it passed. So the next one we can implement how the loss function, or what we call the mean square error loss, and it's nothing but the error between I think there's one thing miss, like 2, because I cannot edit right now. Maybe that's it. So there's missing 1, 2 here because it's a square error, and if you take the derivatives, there should be a 2 here to cancel in the denominator to cancel out the gradients. So I can implement that in NumPy. We can return. We can first do the subtraction of the 2 vectors. And we can take the power of them, and we can compute the mean value. Because those 2 vectors, when they one subtract by another, it's a vector of a residual term, and we do the power, and we do the mean values, and also because we can divide it still by 2 because to keep the gradients quite stable. The final part is we want to solve the linear regression, like as we show in the in the lectures. We need to define the data matrix, do the inversion, and to do the same, and to the best matrix can be computed in this form, in the closed form. So I also give you some hints how to do that. Like first is maybe x transpose is x dot t, and maybe x t x should look like this, and we can do the x transpose x inversion, np dot linear algebra dot inversion. There was a help function here, and I put the function here, and this compute the inverse value for this one, and then we can compute the x invert x top. That's even simpler. It's matrix multiplication with x dot transpose, and return the this one. It's two. And numpy dot those two metrics. And I can run it and to check it if it works, pass. Okay, and I can create a sample, a sample example. For example, I can generate some fake data that the y is the y is 4 times x plus some random noises, and use that data to solve for a linear regression problem, because those outputs and the target and input follow a linear relations. It should looks good. Okay, you can see that. Okay, I solved this question quite good. You can see that you solve for the best weight values, and you put the weight values, and you can visualize the weight values, and you can see how the predicted model is, and you see that it follows the trend quite well. So we solved the first questions, and that's how we do in your assignment. You can I will always leave some visualizations and data checking to see if your function works in your own program. Then we move on to the logistic regression. The logistic regression is something quite simple. Like we first implemented this sigmoid functions. We return the, like as it says, 1 plus n numpy dot minus x, and that is the same implementation as the function itself. And we can compute the gradient as we just show here, like the definition of the gradients. We already derived it in the class. So we just put it here, and we just run the code to implement such kind of computation. So we only have the input, the desired outputs, and the previous weights and bias. So we need to compute the gradient for the weights and bias and return them. So first we need to compute the output for those logistic regression models, like a sigmoid function followed by a linear function. And we compute the error. I can copy that down. And the dw is equal to x transpose matrix multiplication to the arrow. And also I will compute the mean value. It's the same, it's the same that we sum the arrow value. Yes, it's the same way we just compute the mean value of the arrow value as the gradient for bias. And let's see. Yes, we return, as we can see later, we just return the weights and the derivative of the gradients of the weights and bias as the output of the function. And that's it. And check. Okay, I do not do it right. Let's see what's wrong. And I think debugging is also a part of how you do your assignment. And I didn't even myself, I do coding, there was some bugs here. Try. The unpack across. Don't mean. Also, I may need to cheat here. Like I have a, like a ground, like the file with the correct answer to see what happened. Okay, they directly divided by n. Okay, then let me try that. Okay, they directly divided by n. And it's the same, right? Then the also divided by n. And let me see if it's exactly the same. Yes, it's the forward is the same, arrow function is the same, and this is the same. Okay, this time should be good. Okay, pause. And we update the parameters. It's all of course given the same, like you have the initial value of w. We want to update in the direction of the gradients. Just using the learning rate times the gradients and to do the updates. It's the same for the bias. Bias equals and then what we can solve a simple classification problem that we have two classes, like two random clusters, and we have the labels, and we have a learning rate of the 1, and we have a random weights as an initialization and 0 bias. And we repeat the gradients of descent for 100 times. And every time we give the current model and the data, we compute the gradient, and then we update the weights into the new values, and we record the error functions. And let me run this to see if it works. Okay, this gives a very smooth. Like maybe we can try another hyperparameter because the loss curve goes quite well, and the final linear functions clearly separate the two. I can try to do some tweaks here. Like for example, we have a smaller learning rate to see if it works. Okay, the loss function decreases, but it does not converge because we didn't go enough on the direction of the gradient to solve the questions. Maybe we need, if we go with smaller step size or learning rate, we need more iteration to solve the questions. Yes, okay. You can see that it goes, if we extend the training iterations, the results become much maybe become solved. And sometimes in all deep learning or deep learning questions, it's quite important to update the learning rate and other hyperparameters or the training iteration to see if it works. Maybe I can change to other, for example, I make the two cluster closer. How does, okay. Now I have two clusters, but they are slightly more closer. Their center I shifted closer together, and we still have a logistic regression model to solve those questions. It becomes somehow harder because you can see some of the samples are mixing together on some areas of the domains. We see the losses are still decreasing, but it gives us quite decent separation of two classes, but not perfect because the problem itself is much more complicated. Let me still try larger learning rate. That's still the same. Maybe if I do this even closer, like give it even harder problem, classification problem, how does it works? you can see that it's very much inseparable. Those two clusters are clustering together. So we can see that even for binary classifications, if the problem itself getting harder, the optimization gets harder, and even in such case, a linear model can hardly separate the samples we have. I think that might be already the best solution we have. Okay, so after some iterations, the loss does not go any better because those data samples are already mixed together. So I still have, and also we can go to multi-class classification problem, but I didn't implement that in this question because I want to leave it as homework. But we can still finish some of the question here, like softmax function. That's kind of straightforward. We have the we can compute the exponential here, and we can divide by and first we compute the exponential of each element from the vector, and we divide it by the sum. It's the definition of softmax function. Also, we can have the get accuracy, because if I have like the predicted probability and the ground truth labels, I can compute the probability of them. Like we can convert the class prediction into the max value. Okay, we can, in NumPy there was argmax functions for the and it will gives us the predicted class predicted index for the max value within the vector, and compare with labels, and we can let's see, we can make the compare them, and if it's true, it gives it should be a Boolean value, and we can convert it into integers, and it's a number of correct, and and the sum, and if it's equals, it gives yes. It's if it fails, it gives wrong, and we convert the Boolean value into integers, and you sum them together. It means the number of correct predictions, and you can return the total number of prediction is n, and you can return the accuracy of correct minus n, and that should give you correct answer. To check. Oh, hey, it's not props. Okay. Label is not labels. Okay. Object has no to convert it to float. Has no attribute for float. Let me see the ground truth. In how does it do? Okay, it's just the Boolean value. That's okay. Let me try to okay. Good accuracy. number of cracks. NumPy does sum. Okay, let me just copy paste my solutions here to make it works. Predictions, this. Maybe it has the problem with the axis, like. Okay, let's still find the element with the maximum values and in the second axis, and you do the comparison to convert it into 0 and 1, and you do the mean values such that all the correct predicted values sum up together and divided by the total number of predictions. Okay, passes. And you can see that, okay, I have logit, I have a softmax function, I have predictions, and you can convert that into the model confidence. That's the simulated output of the softmax functions, and to see that works. Okay, after doing all of this, you can save the script, and if it's a assignment, you will go to the assignment and you can upload files and select the files that I just fill in. For example, this kind of files, and upload. Remember to change the name to your student ID and the assignment ID, and then your assignment's done. So that's the process how we do this. How we give out assignments, how to finish your assignments, how to submit them, and then we'll automatically this grading process. Right. So yes, I think it's the all of the content I need to cover today. First is the introduction of the course, and second is some introduction of the linear models. The third thing is the coding problem, how to do that, how to submit them, how to fill in those functions and make it works. So I think that's the end of today's lectures. Next week, we will go through the multi-layer perception and how to do gradient backpropagation through multiple layers of neural networks, and how to see that as a more complicated optimization problems. And after the first two lectures, I think most of the basic parts are done, and then we'll shift our attention to like the real modern perspective of this course. And because it's the first lectures, I will like release slightly earlier. And I hope you have a wonderful start of the semester. And thank you. Oh, thank you. Bye-bye.
好像您就是要那个交流的。
对，我会放这个时间。
我意思是您已经把这个内容提到网上了，是吧？
没这个只是一个sample，就是说这是到时候第一次作业和这个不一样，这个是一个sample 的assignment，就是你拿着那个可以看一下，我们到时候
这个还没
对，还没报，对。
刚刚那个也是。
对，那个只是看一下，然后那个答案也在里面，就可以看一下怎么做。然后我下周会 release，说了第二周、第4周、第8周、第10周会 release。然后首先要装一下这个 Option 本吧。
老师，我在哪里后分析？我怎么就报错了呢？就是 我都没有改动，你还练习听。
Function is not defined，
但是
你没有
我前面都导入了呀，那个我为什么第二个下次这里的下次？
让哎，
放在这里。
NumPy is not defined，NumPy 不是在这吧？
对呀，那它不是
重新 restart 一下，可以。restart，有可能它新装的话，你还要 restart 一下，你才能。
直接
这里有啊，
对不起，
呃，
我们那个期中考试，课件写的是第6周，然后那个发的这个
应该是第7周，应该是那个
第7周，
那应该是第7周吧？因为第6周就是
第7周
排除那个的第7周，排除
过年的
过
那
年的第7周啊，第6周排除过年的第
啊，
7周
它好像本来就是过年回来的
啊，对，
下一周
会过年回来下来。
嗯，
呃，
但是这个课件啊，这个课件特别奇怪，那些
那我可能对对。
那课件
哦，OK
写
OK，那
第6周然后 transformer 第7周
应该是第6周，我回去 update 一下，好像。抱歉，我回去
6周那是25号。
啊，对对，应该是2月20号。
那我们考试之前能什么习题复习？
我会发一下，
第6题的，那
应该是第6周。那个 environment 应该不是有，因为已经这么简单了，那个刚刚那个 Jupyter 里面 environment，
对吧？
嗯，
我
有人重开一下，就是关了重开，
也会关，
哦对，关了重启一下 Jupyter，
直接转个题。
对
，OK。
哈哈，第7 要重开，也 not today。So after you see this one, where you notice that your function class is a custom basis, like I like underneath the duplicate I have specific like buildings like your clusters, your classic cases, like so the function is usually use Python. Python is the same. It's the same. You can still use Python for tutorial. Then will be fine. How come there's no such one? Maybe because are you in the right uh it seems that it does not cannot locate the file yeah. You can maybe you can see now. Okay. 当时的还算可能是 都一个一天，但是我的长跟他也会，他那开始是你的 internal 就是我这边独有的一个开始配置，你这里实际上就是我那边是最刷你是配置，就是有个体验，然后都这个啊，但是实际怎么方式可能这个我这里有一个是的。但是这里也有啊，不，那里可以浪费，然后浪费，然后那怎么办？我没需要的，你什么？那我见到他是不这样子，哎，他那个你就导出一个反正这个就去交一个就可以了。但是它这个是 environment 问题，不是 things like 不是。那你
难道是那个男派的？
你只装了男派吗？嗯，看吧，我再说。嗯，already，
对啊，
这里都可以，这里都 work 啊，为什么这里不？呃，为什么？Non-pay is not defined. Non-pay is not defined. 啊，
那个东西，
那个一批放，比方说我们上面的地方，是在这里肯定是Non-pay。我直接换好了。就比如说 IoT 的什么东西的，让我看一下。没事，对对，没事，你打，随便打一个，随便当派一个什么正常的。
直接用了，
啊，对对，可以。
那直接摁7点。
谢谢。我去。
这里用到男派啊，这里
但是他那个 check function 能去点这个 那课里面为什么你这没有啊？我GPT 吧，就这个。
可以用课的，
那 cloud。
香港这边也用不了，就是也要翻墙这样。
啊，是
就不能是。哎，老师，我要问一下那个，就是他那个项目，就是要求是什么啊？
要求，什么叫要求？
就是比如说要做到什么样的一个 级别？因为
是
怎么写的什么 CVP，
随便你怎么做都可以，但是它最后只要叫深入
写个论文。
对，类似